The first presentation will be by Prince Canuma, and it will be about the on-device app intelligence using the MLX. So Prince, welcome, and the floor is yours.
Thank you. Dobry wieczór. Nazywam się Prince Canuma. Książę. I'm just kidding. You thought this would be in Polish? No. So, how many of you here use large language models? I think it's a very generic question, but how many of you use it daily? How many love Claude, GPT-4, all the big ones? Awesome. Today, I'm going to show you a different approach. There's a much better way of using language models, and you can do that on device. I'll show you how to do that. So today's agenda, we'll talk about the rise of small language models. We will talk about how to create these models on your own, using your own resources, your own data, your own compute. And then we will talk about how Apple MLX is actually changing the way you do deployments on device. And then I'll show you just a small demo on how to build this into native apps using a project I built. Now, who am I and why am I supposed to be here? Why isn't it someone else? So this is a little bit of what I've done over the years, close to a decade now, although I look very young. So I'm a machine learning research engineer with experience in the deployments in terms of MLOps, and I contributed to all of these projects here and many others. This is a very special moment for me, and I wanted to share with you guys here. We would not be here today. Exactly a year ago, I actually had applied to join NVIDIA. And thank God they rejected me. Honestly, I love NVIDIA. I have friends that work for NVIDIA, but thank God I was rejected. And I will show you why. Over the course of this year, I built and pretty much added 400 plus models to the open source community, in particular MLX. These models have more than 20,000 downloads, more than 10,000 likes, and they are the top 10 models in the MLX community. Most of them are mine. Now, a little bit about what I've built in terms of MLX. It started with MLX language models, which is MLX LM. I started contributing to the project earlier this year. Then I thought, there is no great way of doing on-device vision. So I would like to run vision language models like Lava and etc. So I decided to build MLX VLM. There was a great success for me as a really big project that I dedicated months and months. It got over 10,000 downloads, close to 200 stars on GitHub. And then I thought, what if I actually join all of this? And I had all these different modalities, language, vision, embeddings, and I could run everything on device. So that's where MLX, FastMLX came into fruition. It's a very interesting way of deploying, and I will talk a little bit about that. And lastly, MLX embeddings, which is about a month old project that I built. So it runs embedding models like BERT and others, and even multimodal coming soon, completely on device. And actually, it was the project that made me top 10 GitHub trending developers building tools for machine learning. So now, this is the year of small language models. You must have heard that bigger is always better. Nah, I think they're wrong on that one. Sometimes smaller can be better than bigger. And here's why. So before we even begin, what are small language models and how can we build them? Anyone, any ideas? The definition of a small language model. Anyone? It's a very simple one. Any guesses? No? Come again? Yes, you're close. Go ahead. You can elaborate on that. He said parameters. So the number of parameters and below 1 billion, close. You're really close. Anyone else? Okay, so the actual definition of small language models are models with a few million parameters to a few billion parameters. And one of my favorite ways of creating them is pruning. So pruning is a project that I actually undertook earlier this year, and NVIDIA actually recently developed a lot of pruned models. But I created this model, the world's first Llama 3 with 6 billion parameters. And this was a model that I pruned Llama 8B. So I just cut off a few of the layers that compose the model to pretty much 30% of the layers were reduced. And now we have a model that has 6 billion parameters. And I actually managed to, with a little bit of continuous pre-training, with just a billion tokens, I managed to get it pretty close to the performance of the original model, which is Llama 8B. So this model now runs with 33% less resources, and it has close to 70% plus of the performance of the original model. So we now have a model that is quite capable and much smaller. And to give you a parallel on why small language models matter, you can look at this graph here by Maxim. He's a really great guy. You should follow him on Twitter. He has really great insights. And this chart here is from, I think, LM or something like that. And what they do is that they compare closed source models with open weights. And you can see here that we have Llama 3.1405 that has performance pretty close to Claude 3.5 Sonnet, which is kind of the current leader behind probably O1. And last week, something very interesting happened. Qwen, which is Alibaba kind of division to build language models, they launched Qwen 2.5. And one of their biggest models, which is Qwen 2.572b, has performance pretty close to 405, whilst having less than half of the parameters of 405. This gives you an idea of, if you really push on small language models, you can have performance close to frontier models. And this can actually run on device. This model right now, you can download it and run on an M3 Max or M2 Ultra. Now, again, why is this important? Number one is faster inference. You can run these models on device, even on your iPhone, and it could run at pretty close speeds as like hosted models. These models can be pretty much fine-tuned to a particular use case, for example, writing, coding, and you can have a model that is pretty good at just that. On top of that, it just has reduced footprint, memory, and lower resources. A great example on the Qwen 2.5 release is pretty much Qwen 14b. It, on average, if you take an average of the scores of the model on the benchmarks, it scores close to GPT-4o mini and higher than Llama 2.170b. That is quite impressive. And this is a model that is pretty small and you can run on your iPhone 15 Pro. Now, I don't believe we will be able to build models like O1 without using SLMs. And I know that's a really strong statement, but if you think about what they're doing, they're scaling the resources during training as well as inference time, meaning adding more latency just to give you a better response. And that latency comes at a cost of resources. Now, what are some of the things that I think they're doing are they're exploring various paths of a particular solution and then filtering them out and finding which one is the best answer. If you have smaller models, you could run hundreds of concurrent experiments during training as well as inference time and provide the answer much better and much faster. But I'm talking about the open source community, the ones that do not have the billions of dollars to spend in terms of compute like the big labs. Now, we now understand why small language models matter and how we can build even more robust models using them. And I want to show you how to actually build these models, or how we are thinking about building these models, how I am thinking about building these models. Here's a project that we launched at RC. I recently joined RC, and I was a part of this project called Supernova. This is our frontier model right now. It was, at least the week it was released, it had kind of the best performance of open source. And the main areas we kind of touched upon to really make the performance gain, I see a lot of people do, for example, data. They focus solely on data, and they try to squeeze as best possible synthetic data. But it's not the only way you can go about this. If you're a true researcher, you can find different ways at the data level, at the infrastructure level, at the model architecture level. And this is where we focused on three main areas to create Supernova. There was data, distillation, and fusion. And I will explain to you what all of those mean. Fusion is the most exciting one, I think. So data. We recently open sourced EvolKit, which is kind of a replication of what Wizard LM Microsoft did with Wizard LM. You have an open source model or even an API, generate the data, and it generates an even more complex question. Instead of saying A + 1 = 2, it creates a way more complex question that forces the model to really understand what it's doing under the hood. And we also open sourced the dataset EvolKit 20K. And this dataset was also used to train one of the versions of Supernova. Then there's distillation. This is a very, very powerful way of building models as well. For example, one thing that we did, we distilled data from, we kind of distilled from Llama 405 to create Supernova, which has around 72 billion parameters. So we actually use the data set to kind of collect all of the logits from 405 to then create, to then use that during training to do distillation on a smaller model. So this is where you'll see, for example, why the performance is kind of slightly higher. But there are two ways of distilling. You have logits based, where you're just calculating the kind of logits of of a particular sample, or you're doing hidden states. So instead of doing just the final logits, you're taking the hidden states of the model and using that to kind of be able to train the model. NVIDIA, I think last week or this week, released Llama something 51 instruct, and what they used was hidden states based distillation. So they prune the model and they kind of distill each layer into the smaller model. Now, and then there's fusion. Fusion was a very interesting experiment. It happened almost merely by accident. I was working on pruning, and then I noticed that sometimes when I prune the model in a particular way, the model produced coherent answers. And then when I ran the same experiment, the model produced completely different wrong answers. And then I said, okay, there is something within the network that can allow you to create a path within the network that provides you coherent answers. And then there's another path that completely destroys language or any reasoning. And then that's where we came up with fusion. A colleague of mine and I were just talking about this bug that I found, and he was like, okay, let's try this. And I said, okay, let me add to that idea and give me like an hour. Within an hour, I had the first version of Fusion. This is version 2, where I fuse 5.3.5 instruct mini with a model we fine-tuned. And this model, the fine-tuned model, is significantly better than the base model by 1%. In other models, we had even like 2% difference in terms of performance. And this is without any training. And another thing that is quite interesting that we discovered with Fusion is that when you do fuse two models, the resulting model has the properties of both models. So for example, 5.3.5 instruct does not do parallel function calling, and actually we fused that with kind of one of our models, and it now has that capability whilst being stronger in terms of benchmark. And Fusion is not only used just for like normal models, you could use this for expansion and as well as pruning. So I do like pruning, but I said, okay, what if I took a model, Quen 1.5b, and then added more layers to it and made it like Quen 1.9? almost 2 billion parameters. And how would that perform? So I created the model, which was this one here. It didn't perform really well. If you can see, like the GSM-Q8 and the MLU kind of is down. So I fine-tuned the model and then merged the fine-tuned model with the base model that I created and using Fusion. And you can see that this model now performs significantly better across the board. And this is without, like the purple one is the one that this like the final model. And this is without training. I just took the training model and the fuse model, and the resulting model is much better than kind of both models. And it's much closer to the kind of base model. I did this with like 40 million tokens. It's not even a billion. It's a very small amount of data. Took around 4 to 7 hours to train. Okay, so now we can talk about RC Nova. We took all of these different areas and we made incremental improvements on them. And this is where we resulted with Supernova and Supernova Lite. So Supernova, our flagship model at RC, performs much better than Llama 405 by a small margin, but it's significant for a model that is at the size of Llama 3.170B. So you can see that there's like a significant improvement in instruction following. And it's the same if you take the average score of Arena Hard, you can see that we are now much higher above Cloud 3.5 Opus with a model that is just 70 billion parameters. And for comparison, you can see that here's, let's say this could be the reference model, and you can see that it scores much lower. Now, let's talk about how you can take the model that you now created using all of these different areas and techniques and actually run them on device. This is where MLX comes into play. MLX is an array framework for running ML research on your MacBook. And of course, nowadays you could even do the same on your iPhone, iPad, and so on, because these machines have become even more capable. But MLX is particular because it focuses only on Apple Silicon. It's not available on any other kind of platform. It's only Apple Silicon. And this is the GitHub repo, and you have kind of the architecture of Apple Silicon device. So you have different cores, and you have something called a unified RAM, and this is what MLX thrives on. It has a similar API to anyone that has ever used PyTorch, Keras, transformers. It's kind of pretty similar in terms of API, even NumPy and others. It's composable, so you can do the same things you could do on the normal PyTorch, like the directed graphs, eager mode, all those different things are available here, as well as this lazy computation. So your tensors don't really materialize until you actually call them. So that makes it kind of works better. It's much faster than, let's say, your traditional torch. And it kind of focuses on unified memory. So it means that your CPU and RAM have access to the same, your CPU and GPU have the access to the same RAM. So it's much faster to move all your different data like tensors. And this is where I was contributing already to MLX, and I thought, I want a way to be able to build native applications, powerful native applications that run using MLX. So I created FastMLX. And FastMLX allows you to create a server completely on your device, and you can serve to any other machine on your network and even multiple machines at the same time. So recently, FastMLX was acquired by RC, and here you can see an example of FastMLX. I just created a machine, an instance using 4 cores of my machine that has 10 cores. Here I'm serving 5.3 mini instruct 4-bit. And you can see I'm serving pretty much all of them in parallel. Of course, the video is a bit slower because of the internet, but if you check this on Twitter, you will see that it's much faster than it looks. And what happened there? We were doing parallel calling. So instead of just instantiating a single model, we instantiated different models on each core, and every single instance of those models was serving a particular request. So a couple of things that I wanted FastMLX to have was an OpenAI compatible API. This would be easier for me to integrate into my existing projects. It should support parallel processing because now I'm not tethered to a particular API provider rate limits. And I wanted dynamic model loading, meaning I want to load different models for particular different parts of my pipeline. So if you've ever built a RAG application, you might need a language model, a vision model, and so on and so forth. With FastMLX, you can do that completely on device, and it would have the same experience as an OpenAI API. So you have different models running on different cores of your machine. Then you have multimodal support, of course, vision, language, embeddings, and now I'm thinking about voice language models and other types of modalities to add, but I'm only a one-man army at the moment, so it will take some time. And then you have modular and customizable. I can easily go and change something either at the MLX level or at my project level, and I can add new models. All of those things are kind of working towards my goals. Now, enough of talking about FastMLX. Let me show you a demo. All right, so let me pull this chair here. Let's go into my terminal. This is my simple terminal. I'm just gonna write FastMLX, 2 workers. This is instantiating FastMLX on 2 servers. It started already, and I can come here. I have a simple Gradio application. It's about 86 lines of code, and I'm just gonna run this project. It's calling the local API, you can see here. It's very similar to what you would get on OpenAPI API. And I'm calling for the language part, I'm calling Quen 2.51 billion parameter instruct in 4-bit quantized. And for the vision model, I'm calling nano level. All right, so it should have started. All right, so here we go. I'm just gonna say, hi. There you go. It's pretty quick, much faster than you would see on video if you try it on your machine later on. This is running at like 100+ tokens per second, completely local on my machine. Unfortunately, I cannot turn off the internet just to show you that it's actually working offline. Then let's try to add a different image. And here I am going to say just describe this image in detail. In JSON, that was a good one. So here it is. This is a close-up of a vibrant yellow and red outfit who appears to be in the midst of a dynamic action, possible jump or leap. The man is wearing a white shirt and black pants. Well, okay, he's talking about probably this guy here. And his hair is styled in long, which is a pretty long hair. You have the entire description, and this is running completely offline, and it loaded both of those models. To show you that, here you can see that it actually loaded the first model, and then it loaded the second model right here. And it served those requests completely on device. Let me close this off, and we can go back to our presentation. A quick demo, but I'll show you even cooler projects that people are building with FastMLX. All right, so here are some cool use cases that I've seen ever since I launched FastMLX. The first one, I actually built it, which is a home hub AI API. So here I'm serving a model from my M3 Max into my MacBook Air over Wi-Fi. And that's how quick it is. So it has streaming built in. You can build an iOS application and then just point out to this particular API in your network, meaning the IP of your machine, using the same kind of V1 completions endpoints, and FastMLX will serve that to your different devices. And here's another really, really cool one. I saw this week is from Matthew, and hopefully he will join RC. I had a talk with Matthew this week. He built a autonomous engine on Minecraft that is at this point is trying to cook. So it put the oven and is going there to kill the lamb or whatever it is, and then trying to cook it. And this is running using Qwen 2.5, a 30 billion parameter model running on an M1 Pro. So this is a MacBook that is quite old now and only has like 32 gigabytes of RAM, and it's running this instance doing this. And more recently, actually, when I met him, I think a day ago, oh, the video is gone, or the picture. He actually built a local agent that can see using the Vision API of FastMLX. And also that agent you saw can now see and tell you the details of the game world it's seeing. You can check this out on Twitter. His Twitter is at MWRights_. He has all of those, and he actually tagged me on those posts. Wow. Okay. So I had an image that was actually showcasing FastMLX distributed. So I'm running a mixture of experts model from my Mac using my MacBook Pro and my MacBook Air. So the MacBook Pro is running all of the experts, and the M1 Air is running only the backbone of the model, and I could achieve like 4 tokens per second using that distributed interface. Meaning if you have a really large model that does not fit on one machine and you have an extra machine laying around, you can actually use all of your devices to run inference. I will post the link to the slide with the actual image here. I'm using Canva, so internet. So the first one is distributed workflows. Then there is task LoRa's. How many of you here watched Apple Intelligence event? How many? Okay, cool. So you remember you saw that Apple is actually using a single small language model that's about 3 billion to 7 billion. And all they're doing is that they're changing the task LoRa. So they have a LoRa for writing, they have a LoRa for different modalities, and they're changing that at the moment you're trying to access a particular application. FastMLX already has the infrastructure to do this. And I just thought that it would be nice to add this, and you'll be able to, hot swap LoRa's. So meaning you can have one single model that you have all these different LoRa's for, and you can hot swap them at inference time. So for example, if you want writing, you have a LoRa for writing or coding and so on. Then there's on-device training. This is already supported, but currently I'm trying to add this for vision. It's coming, and also I talked about more modalities that are also coming to FastMLX. So conclusion. Small language models might be all you need. Yes, the frontier models can provide you really, really great answers, great interface, but you only need to collect a small data sample to be able to train your small model to do exactly what that frontier model does for you or for your customers. And of course, it's easier on latency, scaling, resources like money. Not everyone has all the GPUs in the world or money to pay for APIs, because at a certain point, those APIs become really expensive. Then you have, I showed you different ways on how to build these models, improving on more areas than just data. So looking at the architecture, distillation, and all this frontier research. And then, of course, with FastMLX, I'm trying to build or pave the way for on-device deployments, meaning in the future, you'll just be able to deploy your application and run FastMLX behind the scenes, and your users won't even know that that this is like running. They won't even feel, because as the pretty much Apple Silicon machines become more powerful, you could do this with much larger models at each iteration. So this is the future. This is what I dreamt of. And part of the reason why I built FastMLX is because I was building a project called Lisa Pro. It's a local coding assistant that pretty much uses agents to do it, but I didn't have any good way of actually orchestrating all of this. So I built FastMLX to solve that use case. And I shared it with the world because I believe in open source and I believe in sharing openly, and we all collectively can become better. Now, what are you going to build after this talk? I'm super excited to see. If you build something really cool, just tag me on Twitter at Prince Canuma, and I will be more than happy to share it and put it in our list of really cool projects for FastMLX. Thank you. That's a wrap. Any questions?
If you have any question, please raise your hand and I will come with microphone. I'm coming.
Hi. So I would have a question about the performance that you mentioned.
Yes.
The base model with another version of it.
Mhm.
So I was wondering what kind of like score were you using to compare it? Was it only based on some memory usage or computation usage or maybe some sort of validation metric?
You're talking about the models that we build like with training?
Yeah. You mentioned that there were like a base model, like
Yeah.
and then you have a sort of different version.
Yeah, so those were evaluated using the open source kind of leaderboard benchmark. So there's a benchmark that kind of computes reasoning, has a score for reasoning. It asks the model a bunch of questions and gives a score to the model on those all different capabilities. And then you can kind of take the average of that to have the average score, or just improve, try to see which area of your model is not performing well and train specifically for that. Yeah,
Okay, thank you.
sure. Questions?
Questions?
Don't worry, I don't bite.
Hey, I was wondering about the inference speed. If you were to, for instance, because now you can actually deploy MAX to cloud, right? I think with AWS, for instance.
Sure.
So if you were to choose today, in terms of like inference speed, whether to deploy to like a model to M architecture or like NVIDIA GPU, do you have like any benchmarks which compare one to the other in terms of, I don't know, speed and maybe the cost as well?
It depends on who you're trying to serve or your particular use case. If you're trying to serve a model that's like 400 billion parameters, it would be better for you to do that on the cloud using not only one, but probably a few, like 50 to 100 GPUs, so that you can serve, let's say, 1 million customers or so on. But if you're building a native application where you have particular use cases where the small models can actually address, like writing, coding, and so on, you could deploy that onto the customer side, and you have zero cloud costs. All of the costs are incurred from your customer. The internet, the internet for APIs or whatever that your agent might use using your model, or the energy. And Macs are super efficient compared to like if you have a desktop with NVIDIA GPU. Macs are a bit more, I know it should be taboo to say this here, but they are more efficient in terms of energy. So the performance per watt is actually significant. We're talking about just that machine alone, it's like 14 teraflops or something like that. So you could launch like a 72 billion parameter model there and run it normally. So I would say look at your use case, find a way, for example, to customize it so that your customers can incur all the costs on device. But if you have customers that use different platforms rather than Macs, you potentially just want to use the cloud. It just depends on your use case.
More questions?
Anyone of you use Cursor or uses Cursor? Yeah, did you know that Cursor is actually running a 100 million parameter model completely on device? Most of the users of Cursor don't know that. Like when you see the autocomplete thing, etc., it's not running cloud. It's running an actual model that they trained just to do that particular task. And that model is pretty good. So imagine those kind of use cases. And then, of course, they have access to a bigger API if you want to chat on a particular engineering problem that you might have. So that's kind of how I'm thinking about this. Questions?
Yeah, it's a quick one. So those big companies, they release those models for free, right? But they have the directors that make money out of them.
Yes.
Stuff. And they want to like, what do you think? Why are they releasing it now for free, and how long is it going to be?
I think it's gonna stay for longer because there's a ceiling that you can do. You're gonna have when you have resources like NVIDIA or even like OpenAI and so on. There's a ceiling. That's why open source is thriving. Open source community is very, very scrappy. We can find ways to optimize these models that the labs would eventually come up with them, But if you look at, for example, what OpenAI has done over the years since they released their models, they look at what the best research is, what the best products on top of their APIs are, and they build those products into them. Like they benefit as well from the open source community. So I don't think that's gonna stop. There's a added benefit to releasing these models openly. You can find all the bugs and problems much faster than you would in a red teaming.
At the same time, they're released between two, but they never released any other models.
But look at without OpenAI releasing their models openly, the community already caught up without them doing that. So there's always gonna, I believe that both depend on each other. Closed source and open source depend on each other. Of course, closed source is mostly the frontier. They are ahead of everyone, but they give us a glimpse of what we can do, and we figure out cheaper ways of doing what they spent billions of dollars. I bet you within the next 3 to 6 months, we're going to see an O1 level model completely open source. Yeah. That's a really good question. Questions? Any more questions?
I don't see. So thank you, Prince.
Thank you.